Okay, so continuing on with our long Unit 2, now we're going to cover two-dimensional motion. So we're sort of mashing the first two things we've done together, vectors and kinematics, applied to two dimensions. And we're going to tackle really velocity problems separately without acceleration, and then mainly projectile motion problems. But just things to remember: velocity is a vector. In one dimension, when we were doing the kinematics, we really just kept up with that direction through positive and negative numbers. We say right's positive, left's negative. But in two dimensions, now we're going to bring in our trig and our angles again. Remember, the average velocity equation is a vector equation. And we can apply it to two-dimensional problems by considering one dimension at a time. So the direction and velocity, the direction for velocity and the direction for distance, really displacement, must match to use this equation. That is really important in projectile motion and these velocity two-dimensional problems. You're welcome to use the kinematics, you're welcome to use this equation, but these directions have to match. If this is east, the velocity is north, there's no way we're solving for time. So which ship crosses the river first? Both are going 5 meters per second across the river, but this boat on the left has a current pulling it west at 4 meters per second. No current on the other side. Common guess is to say that, well, this one's going faster overall, which it is, so this one should cross the river first. But it's not true. They will both cross the river at the same time. And one of the clues there is simply that word across. The question was about across. Well, they actually have the same speed across. Current does not affect how fast this ship will get across the river. Now, granted, it will end up, down here to the left by the time it makes it across the river. But as far as getting across, it's going to take the same amount of time. So perpendicular motion like this does not affect each other. So here's a kind of common river velocity current problem, I guess. So the ship heads directly across a large river, which has a current of 4 meters per second. The boat makes it across the 7.2 kilometer wide river in 20 minutes. What was the resultant velocity of the ship? What's the resultant displacement of the ship? And what was the displacement downstream? So notice there are specific directions on all these questions. I care about downstream or the resultant. So I'm going to do a little sketch, list my info, although being very clear what direction I'm talking about, and see if we can attack these problems. So we got current of 4 meters per second, 7.2 kilometers wide, 20 minutes. Okay, so here's a little sketch. Here's a given info. I am calling downstream to the right. Does not matter which way you make it. Wasn't specific in the problem. And here are sort of letters I like to use as little subscripts to help me keep my information straight in a river problem. A for across the river, D for downstream, and then R for resultant. And you can use whatever else makes sense to you. So the velocity downstream was 4 meters per second. The displacement across is 7.2 kilometers. And of course the time is 20 minutes. So going back to my problem for a second. First question is, what was the resultant velocity of the ship? So in most of these river-based problems, the boat's probably trying to go across, either wind power, motor, who knows. But then there's some current probably pushing it downstream. So in my picture, my boat is definitely going to be pushed downstream, and these are really the components of this overall vector. This is the resultant velocity that I have drawn here, moving off at that angle. That's the combination of, you can call it the x and y components, but really it's the velocity downstream and the velocity across. So if I want to get the resultant velocity, I have two choices. I can find the components of it, the velocity downstream, the velocity across, and do Pythagorean theorem, all right, to get that resultant vector, just like we did last unit. Or the other way to solve this problem would be to know the resultant displacement and the time. So I do know the time. I don't know the resultant displacement yet. In fact, that was question B anyway, the second question. So I'm going to take the first approach. I'm going to try to just use vector addition, knowing the downstream velocity and then the across velocity. I already know the downstream velocity, 4 meters per second. But I can pretty easily find the across velocity since I know the across displacement. And there's no acceleration in this problem. So this equation really is the key to my success here. I just need to make sure I keep my directions consistent. Any velocity that I plug in here has got to match any displacement there. Okay, so I've listed my given stuff. I do note that I've got unit issues. My downstream velocity is meters per second, but I also have this displacement in kilometers. I have this time in minutes, so I do need to change all those things. Kilo, again, one of those prefixes really should know. That's a factor of 1,000. So 1 kilometer is 1,000 meters. So I know that's 7,200. Move your decimal 3 times. And then minutes, I'm going to stick with my usual seconds. So just multiply that by 60. 1 minute on the bottom, 60 seconds on top. So that's 12, 2 zeros. Okay, so I've taken care of my units. My units now match. And now I'm going to plug in to find first the across velocity, which I know is not a question, but we need to know it to finish the problem. So velocity across equals displacement across over time. So velocity across what I want. Displacement across was 7,200. Sorry, my mental math a little poor. All right, so 6 meters per second is the velocity across. Again, haven't answered the question yet. The question was resultant velocity of the ship. But now I know the sides of my triangle. Downstream velocity was 4, across was 6. So just do Pythagorean theorem with 4 and 6. You get 7.2. So that is the first answer. The resultant velocity is 7.2 meters per second. But I'm still not completely done with that answer. That's just the magnitude. That's the hypotenuse of that triangle. Velocity is a vector. So I really need some sort of angle here. And it just depends on how you want to describe it. I want to find that angle, and I will just say sort of with the bank. You know, the bank is here. We're going off at this angle here. So 7.2 meters per second at such and such angle with the bank. You could have found maybe the angle up top and said maybe with across. Since we don't really know if downstream was ever left or right to begin with, can't really get more specific than that. But again, we did Pythagorean theorem, we get 7.2. And now I'm just going to do inverse tangent, which hopefully we're all familiar with from the first unit, to get the angle. So inverse tangent 6/4 is 56 degrees. So at 56 degrees with bank. Okay, so that's my first answer. Next question will be pretty easy. And I really could have done that last question already too. But let me erase, give myself a little room. Okay, so the resultant displacement I could get just simply using this equation. Now that I know the resultant velocity, just plug that in. You also could have found the displacement downstream, like how far does it float downstream if it's going 4 meters per second and is taking 1,200 seconds to do that. We could have found the displacement downstream because we know the displacement across and done Pythagorean theorem with those answers. But this should be just one little step quicker. Of course, I am assuming I am right about my resultant velocity. All right, so 7.2 equals displacement resultant divided by 1,200. So 7.2 times 1,200 is 8,640 meters. I don't think we're right about that. And since it's a vector again, technically I should put that same angle on there at 56 degrees with bank. All right, so there's another answer. And again, the resultant displacement would be, from here where it started, final minus initial, up here. So let's say it traveled that whole sort of orange distance. That's the displacement. That would be 8,640 meters. Should make sense that it's longer than the across value, because again, that's sort of the hypotenuse of our triangle. All right, what was our last question? What's the displacement downstream? All right, I'm going to use the same equation, except I'm just going to change all this info to downstream info. Erase that too. Oops. Okay, so I'm going to use the velocity downstream to get the displacement downstream. Velocity downstream is 4. So 4 times 12, throw on a couple zeros, 4,800 meters, and you can write out the word downstream as your direction. Voila. A lot of questions in that problem. Main ideas, again, you are welcome to use the velocity displacement over time equation. We're about to use all the kinematic equations, but directions have to match. I cannot plug in velocity across to expect to get the displacement downstream. Just would not work that way. Realize we also have sort of vector components when we're trying to find our resultant, whatever, resultant velocity, resultant displacement. So we occasionally need to do the Pythagorean theorem as well, just like we did in the vector unit. And if you're ever solving for something that's a vector, please put a direction on there. We also did inverse tangent with this 6 and this 4 to get the angle. All right, that's a long two-dimensional velocity problem. Now let's try throwing in some kinematics as well. Okay, so pulling in the kinematics, it's going to involve an acceleration course. Kinematics were based off of motion problems where acceleration was constant. An easy way to do that is when we talk about gravity. So just a reminder here, projectile fired straight up has a velocity of 0 at the peak. Okay, we know that. They're also symmetrical, so if it takes 5 seconds to go up, it's going to take 5 seconds to come back down. Again, ignoring air resistance here. And this little video clip just shows, I believe, dropping the hammer and the feather on the moon, which we saw in 9th grade physical science anyway. But without air resistance, of course, they would take the exact same time to fall. Okay, so we're going to pull these ideas into projectile motion. A projectile, things that are projectile. Somebody who's hitting a golf ball, a cannonball fired off a ship, somebody just throwing a baseball, but anything that follows a trajectory, this typical sort of little parabola here, shape of a projectile. Things to remember. Horizontal and vertical motion are independent, just like when we did the river problems across downstream, those were independent things. Same with projectile motion. And again, that boat problem, of course, we said takes the same time for each of them to cross. The cross information is all the same. All right, what do we call vertical acceleration? Okay, gravity. Does it affect vertical motion? Yeah. Does it affect horizontal motion? No. So if we are dealing with horizontal motion, we would simply use our basic displacement over time. This is the equation we use when there's no acceleration. We cannot use this when there is acceleration. Okay, that's a huge mistake that I commonly see in this unit. Kinematics are for when something's accelerating, vertical motion where we have gravity, but displacement over time is sort of your basic horizontal equation. There's no natural horizontal acceleration. If I'm bowling and I let go of that ball, when it's rolling down the alley, there's no gravity pulling it sideways faster and faster. It is essentially moving at a constant velocity, of course, until it hits the pins. But there's no horizontal gravity. There's no natural force sideways. Okay, I do like to draw the acceleration and velocity vectors on this little trajectory. So I'm just going to start with gravity. Now gravity is not a velocity vector, but that's okay. We know that gravity is the same anywhere on this little trajectory. So we could assume this was maybe that golf ball that was chipped. Gravity is always down. I'm going to make it blue. And it should always be the same size, to the best of my drawing ability. Okay, so gravity vector, anywhere where that golf ball could be, is always trying to pull the golf ball down with the same magnitude, same 9.81 meters per second squared. All right, then I'm going to actually draw sort of the overall velocity. You know, at first, this golf ball was hit with the steepest angle. So I'll start off to the right. Something like that. Again, it would really be like the tangent line to this parabola here. You know, if we just continue drawing in a straight line at this moment, you know, what would it look like? This is just the overall velocity at the peak, just for that instant. It is just horizontal, because remember, that's the instant where it stops going up or down. So that's referring to that instant right there. I know my vector has some length to it, but I'm just referring to that little instant right there. Okay. So those are my overall velocity vectors. Of course, the angle gets more shallow as it goes towards the peak. Then magnitude, of course, gets bigger as it falls back down. But now I want to throw in the x component of the velocity. And here's, again, the idea. There is no horizontal gravity. There's nothing speeding it up or slowing it down sideways, left or right. So its velocity, left or right, should always be the same. So this is Vx. This is Vx. Again, I'm doing an x component. Notice, decently to scale, these are the same size. Here, V equals Vx is the same thing. I'm trying to make that the same size. Down here, we've got Vx again. And Vx again. All right. My scale's not perfect at the end. But all those little Vx's should be the exact same size. There's nothing accelerating them to make them bigger or slowing them down to make them smaller. Vy is certainly a different story. The y component, the vertical component, the component that is affected by gravity, keeps changing in magnitude. So of course it is up in the beginning, it's up here as well, but much smaller. At the peak, Vy is nothing. There is no Vy, no up, no down. Again, for that instant. Falls back down, so Vy reverses directions. Now it is down. And of course, the largest value at the end. Again, these are symmetrical, so the vertical velocity that is up at the very beginning has the same magnitude as the vertical velocity that's down at the end. So stuff we know, as a recap, G is always the same size, always points down. Vx is always the same size, always points right, again assuming my projectile was hit to the right. And Vy, of course, decreases towards the peak, it's 0 at the peak, and then increases as it falls back down from the peak. So take a second, make sure you got all that copied down. Sorry if you don't have different colors. All right, just pulling in a couple graphs. What if I were to graph the x velocity versus time for that projectile? So how did the x velocity change? So anyway, think about the projectile vectors we just drew. You know, the vertical velocity, sorry, the horizontal velocity, the x velocity. Did it ever change as time went on? As you know, we went up to the peak and fell back down? No. The vertical velocity was a constant thing. And it was always right, so it was always positive. So something like that. Now, the vertical velocity, very different story. Magnitude started out big and up, so positive, but ended up big but negative. And somewhere in between at the peak, it was 0. So our graph should look like that, where this would be the peak time right there. Also, of course, we should know our slopes too. There's no slope here, but this slope is clearly negative. And remember, the slope of a velocity graph is acceleration. So as we remember, slope of a velocity graph should be negative 9.81 meters per second squared. It should be acceleration, which we could make up some numbers to make that true, but just know that it should be gravity. All right, a couple classical problems to discuss. Sorry, this is the best artwork I could come up with. But it says your friend, so this is you, this is your friend, 1920s gangster. Your friend fires a gun horizontally. At the instant he pulls the trigger, you drop a bullet from the same height. Which will hit the ground first? Now true, we do need to ignore air resistance, because this one might act sort of like the wing of a plane, Bernoulli's principle. There'd be a little lift there. But ignoring air resistance, they hit at the same time. Vertical acceleration is gravity on this bullet. Vertical acceleration on this bullet's gravity as well. And they have the same vertical information to begin with. Neither was shot up or down. So the vertical velocity originally is 0 for each of these. Yes, this one that's fired out of the gun has a huge horizontal velocity, so when it hits the ground, it's going to be way over there, way far to the right, but it will still hit the ground at the same time it takes this one to fall. And hopefully we'll show that in just a second. Not with real gun. Okay, so here's a little demo of the firing the gun, dropping the bullet classical problem. We have this little spring-loaded device. And I have to sort of line it up off of my table, but we're going to kick one marble just straight off onto the floor. And at the same time, you know, while that marble is getting kicked onto the floor, this one's going to fall. So usually we just listen, but hopefully we can kind of zoom in and see this happen. But they should hit at the same time. So listen, see if you can tell there's just one bounce. And also hopefully we can actually see on the floor that they hit at the same time. Next classical problem. I don't know why this is a classical problem, but shoot the monkey. Classic physics problem. Says you are aiming your gun at a monkey that is hanging from a tree. At the instant you pull the trigger, you startle the monkey and it drops from the tree. Will you hit the monkey miss above or miss below? One way to think about this problem is, well, what would happen if the monkey wasn't startled? If the monkey stayed there? And you are shooting at the monkey are you going to hit the monkey at all? Well, of course, depends on the power of your gun, but you will not hit where you're aiming, assuming you don't have some sort of distance correcting scope, etc., etc. If you are aiming at this monkey and it does not drop, well, your bullet is going to turn into that little trajectory. So it's going to start to fall, fall, fall. And no matter where you aimed on the monkey, you are going to hit low. So you may miss the monkey altogether if the monkey does not drop. If the monkey does drop, you actually hit exactly where you would have aimed. Sort of like the monkey is falling into your bullet. And I'll show you a little video on that too. But if the monkey does drop, you hit exactly where you aimed. You'll hit the monkey. If the monkey didn't drop, then you would miss low, or at least be lower than where you were aiming. Similar to this problem, a hunter aims directly at a deer, same gangster. Where will he hit the deer? It doesn't matter how far away he is. So, sorry, I apologize if these are some morbid examples. But let's say this hunter had like this laser beam sight on the deer. You know, he's aiming straight at the deer. No matter how powerful his gun, no matter how fast that bullet is coming out of his gun, it is still going to fall a little bit before it hits the deer. So it might be doing this. And maybe he gets Bambi in the knees. Sorry, Bambi. So no matter how fast the bullet is fired, it's still going to hit lower than where he aims. Now, if he's, a sniper in the military, they have little scopes that they've got to sort of input their distance, based on how far away they think they are from the target. It will correct how they aim. But without something like that, if you just sort of aim straight, you're not going to hit dead straight. You're going to hit just a little bit lower than you think. Doesn't matter how far away he is, sure. The closer he is, the closer he'll be to hitting his target. But even incredibly close, he's still going to hit lower than he's aiming because that bullet has to start falling. All right, so those are our classical projectile motion physics problems. Again, sorry they all involve guns. But interesting to think about how, regardless how fast the bullet's fired horizontally, it's still going to fall at the same rate as one that were dropped. Okay, so analyzing some projectile motion problems, we just have a couple problems left to finish up. We've got to analyze components of velocities. We drew these angled velocities on our projectiles. We will never deal with velocities at an angle. We only want to deal with the horizontal part of it and the vertical part of it. So we've got to find, like I said, horizontal and vertical components of our velocities. For horizontal information, stick with velocities displacement over time. For vertical information, then use your kinematics. Remember, trajectories are symmetrical. Remember, the acceleration that's there is gravity. And remember, you can use the kinematics, because those are your acceleration-based equations. And of course, the peak velocity is 0. Okay, so first problem says a ball is projected horizontally from the edge of a table that's 1 meter high and strikes the floor at a point 1.2 meters from the base of the table. Okay. What's the initial speed of the ball? And how high is the ball above the floor when its velocity vector makes a 45-degree angle with the horizontal? Okay, one more time. Ball projected horizontally off the edge of a table. strikes the floor 1.2 meters from the base of the table. Let's just start with A. What's the initial speed of the ball? Okay, so it never hurts to have a good picture. Certainly recommend you draw a picture for any projectile problem. This one's really half a projectile problem where we're starting at the peak. So the ball is basically doing this little half a trajectory. We know the height to the peak, and we know this distance along the ground, which is really horizontal information. Okay, so I'm trying to find the initial speed of the ball. And when I list the information I know, I usually do it with vertical information and horizontal information kept separate. So I still want a list of all my given stuff, but I'm going to keep it separate as far as horizontal and vertical. And in fact, my question is, what is Vx? Okay, what is that horizontal velocity? And I know that because it has to be horizontal at the peak. This is half a projectile. So the only way I can solve for this particular question is to know horizontal information and to use velocity as displacement over time. So do I know the displacement in the x direction? I do. The displacement in the x direction is 1.2 meters. Do I know the time it took to go that 1.2 meters? Sadly, no, I don't. And that is almost always the way projectile motion problems work, is that you need to find the time in one direction and use it in the other. And time is not a vector. So in the same amount of time it takes to go 1.2 meters to the right, it is also falling down 1 meter. Those times correspond. So if I can find the time vertically, I can find the time horizontally because they're the same, and I can solve my horizontal problem. All right, so I'm stuck for the moment in the horizontal direction, but let's go ahead and solve for what I know in the vertical direction. Or what do I know in the vertical direction? Well, I've got this 1 meter. That is clearly a displacement, meters, distance. I'm going to call it delta y. But I do need to be a little careful about signs. You know, was it up or was it down? Well, it fell down 1 meter. Its displacement was negative 1 meter. And that looks like all the information I know vertically. But I really know two more things, even without them being stated in the problem. The fact that this is half a projectile and we're starting at the peak means that my initial velocity, or my v naught, y, was nothing. There is no vertical velocity initially. It will immediately have velocity as it falls down. But initially it's nothing. And since this is a problem where something's falling, I know the acceleration, the ay, is gravity. So in any projectile problem, you can always list the acceleration vertically is gravity. Okay, so again, my plan of attack was solve for time vertically, plug it into the horizontal information, and then I can solve that horizontal answer. All right, so when we're using the vertical side, vertical information, you've got to use your kinematics. Okay, this is an accelerated problem. I cannot just use displacement over time. So I'm thinking through which kinematic, let's see, really doesn't have Vf in it, the final velocity, or just V, because I've got everything else. So, you know, take a second, you'd look through your list, and we would find let's see this one. V naught t plus 1/2 at squared is my displacement. My units are already good to go, thankfully. I've double checked my negative signs. Now I can just plug on in. -1 equals, really this goes away because that was 0. And then just solve for time. Don't forget your last step is going to be a square root to get that time by itself. You should get 0.45, which based off the units I already started with has got to be seconds for time.
The classic demonstration for projectile motion is shoot the monkey. And I would be remiss if I did not have shoot the monkey when I talked about projectiles. And I have the monkey of science here on hand to help us do the shoot the monkey experiment. He's got a cool little headband. That's so a blindfold so he doesn't have to watch the danger. And a nice breastplate to keep him safe. All right, what we're going to do is we're going to take a metal ball, steel ball, we're going to load it up in this air gun here, okay? And then we'll aim it at the monkey and see if we can hit him. Now this is not just for entertainment purposes. We're not just shooting the monkey for no reason. The question is, if we shoot a monkey, all right, if we aim at the monkey of science, right, where do we want to aim when we shoot the gun so if the gun startles the monkey and he lets go of the tree or whatever, right when we shoot the gun, where do you have to aim so that the bullet hits the monkey when it's falling? Okay? Do we have to aim below the monkey so that when the monkey's falling, he falls in and gets hit? Do we have to aim above the monkey so that the bullet arcs and hits the monkey? Or do we aim right at the monkey? And that's the eternal question. So let's get set up. We've got the gun loaded and trigger on, and I'm going to go put the monkey of science up, ready to be hit. So I'm going to aim right at the monkey. We're going to see what happens. Here we go. 3, 2, 1. There we go. We hit it. Here we go. Trying to see where it's going to go. When I aim right at the monkey and launch the ball, right, they end up hitting each other. Okay? So why is it aiming at the monkey do better? Well, you can think about it. If they were really close together and I push the ball sideways, because sideways motion is not anything to worry about when you're calculating up and down motion. We can kind of keep them separate, right? So the horizontal motion of the ball can be ignored, and we can, so if it was flat, the ball and the monkey shooting at each other would fall at the same rate. Right? And then if we shoot an arc, they still match up, okay, if I aim up at an angle, because it gets this little arc and comes down and hits the monkey at the same time. All right, so you aim at the monkey. It's, in some ways, you can see that they both have the same acceleration frame. They both have the same gravity. If one experienced gravity different than the other, then they wouldn't hit. Okay, so that's the easiest way to explain. But the cool thing is that you just aim right at the monkey, and if it starts falling when you shoot the bullet, then they'll hit at the same time. So something to take away from this, though, is if you took a gun and shot a bullet sideways, and you had a bullet in your hand and you let go of it and let it fall to the ground, which would hit the ground first? It turns out, if you ignore the spiraling of the bullet and a couple other details, but it turns out that the bullet will hit the ground shot from the gun. The bullet from the gun will hit the ground at the same time as the bullet that you drop with your fingers and let it fall straight down. Right, as long as the bullet with the gun doesn't hit anything, and we don't want it to hit anything. So if it just went straight and eventually hit the ground, and a bullet, you'd let go of it and went straight down, they would hit the ground at the same time. All right? Be careful with guns, and remember, only experienced monkeys of science should be hit by projectiles.
Okay, so now that I know the time it takes to fall 1 meter is 0.45 seconds, I know that that's also the time it is traveling to the right, 1.2 meters. So I can plug that in now in the x direction. And there's only one equation I'm going to use in the x direction ever, and that is velocity of displacement over time. And that gives me .6 repeating meters per second. And I'll throw it right just for good measure, just for my direction. Okay, so that's my answer to the first part. The initial velocity of this ball is 2.6 meters per second, just fired straight off to the right. Immediately will start fall, but that's the initial. Let's see. So I'm going to plug that in now here. So my x information is complete. And we're going to look at the second question. It says, how high is the ball above the floor when its velocity vector makes a 45-degree angle with the horizontal? All right, kind of a weird question. How high is the ball above the floor when its velocity vector makes a 45-degree angle with the horizontal? All right, so when its velocity vector is at a 45-degree angle, and I would probably say it's like here-ish. You know, and think of how we drew those vectors on that trajectory earlier. So it's sort of like a tangent line here, going out, down. We're calling this 45 degrees. So 45-degree angle with the horizontal. That is a horizontal, so that's fine. What this tells us, though, if this is a 45-degree angle, of course, this is also a 45-degree angle. And if this is Vx, and it's a 45-degree angle, Vy at that moment, that has to be the same thing. So we just found out that was 2.67. Well, same for Vy at that moment. I'm going to throw in a negative sign because it's down. So none of this information has changed, except solve for a different delta y now. I take that back. And the time is not the same time. It would obviously not take the full 0.45 seconds to get there. Maybe it's exactly halfway, but unlikely here with an accelerated situation. Okay, so delta y is actually the question. And in fact, it says how high above the floor is it. So we're going to have to come back and think about what that really is meaning. Our initial velocity is still 0, but our velocity at this moment is negative 2.67 meters per second. And let me get a little space and clear out this stuff. Okay, so our question is sort of what is the displacement? I know that the velocity at the moment where I want to find this displacement is negative 2.67 meters per second. So it's this height that I want to find. Technically, if I'm finding the displacement though, I'm really finding it from here, final minus initial. This is actually what I'm solving for, delta y. If I'm using, technically, if I'm solving for delta y, I'm really solving for this distance. Sorry, my picture's getting a little messy here, but final minus initial, how far down did it go between the moments of initial velocity is 0 to final velocity is negative 2.67. So that's going to give me the drop, between these two values. So this is going to be my squared equation. Of course, that goes away. All right, solve for delta y. We get negative 0.36. Negative should make sense going down. Again, that is how far it is dropped from the top of the table. To answer how high is it above the ground, well, if the whole tabletop height was 1 meter, we just need to do 1, minus 0.36. And then at that moment would be 0.64 meters above the ground. A little tricky question with that 45-degree angle thing. But whenever the velocity makes a 45-degree angle, that does tell me the components are the same. So it gave me that Vy component. And then I was able to use what I already knew to figure out how far it had dropped. Okay, so that's a sort of half projectile problem where we're starting at the peak. Remember, peak velocity is always 0 vertically, and horizontal velocity never changes. Okay, so now let's do a full projectile problem. Okay, so last problem, it's out of the book. It says a ship maneuvers to within 2.5 times 10 to the third meters of an island's 1.8 times 10 to the third meters high mountain peak and fires a projectile at an enemy ship 6.1 times 10 to 2 meters on the other side, as illustrated below. If the ship shoots a projectile with an initial velocity of 2.5 times 10 to the square meters per second at an angle of 75 degrees, how close to the enemy ship does the projectile land, and how close to the peak, or how close vertically does the projectile come to the peak, I guess, the mountaintop here. Okay, so this is a pretty helpful picture. I'm going to try to keep that. So we want to know two things: how close to the enemy ship, how close to the mountain. And again, it looks, based on the picture, it looks like, clears the mountain, obviously, so it's got to be higher than 6.1 times 10 to 2. And it looks, according to the picture, like it is long. So we shall see. Okay, just trying to give myself some room, trying to keep this picture because it has all the information right here. We got a lot of scientific notation. You can keep it. I'm going to just go ahead and rewrite things without scientific notation, like 10 to the 2, that's 2 zeros, that's times 100. So it's a little easier for me to think of this as just 250 meters per second. 10 10 to the third, 1,800, it's 3 decimal slides. Down here we've got 2,500 meters plus this additional 610 meters. And that was the distance just to where the ship was. Okay, and we have a picture, so that's nice, but I am going to redraw the velocity part of it. And I highly recommend you do this. Anytime you have a full projectile and you are given an angle, if you are given an angle, you immediately need to find components of that vector. So I know I have this trajectory. I know the initial velocity is 250 meters per second. And the angle there with the horizontal is 75 degrees. I need to find the components. I will not use the 250 meters per second in the problem other than to know these components. So please, once you find these components, just ignore the 250, remove it from your mind. You only need the components to continue this problem. All right, so this is a trig problem. We've done our triangle math before, so we should be able to find the x and y sides. I'll just do the x real quick. This is the adjacent side, and I know the hypotenuse. This is going to be a cosine thing, so I know that cosine, of my angle equals, the adjacent over the hypotenuse. So if I want to get Vx, I need to multiply that hypotenuse over. I need to be doing 250 cosine of 75, and that's Vx. All right, so I get 64.7 meters per second. 250 times sine of 75, we'll give me the other side, is 241.5 meters per second. Okay, so I found the sides of my triangle. If you are given an angle, again, to a projectile motion problem, that should be the #1 first thing you do, find your components. Guaranteed you're going to need to know one of them. Now, I would just list my info. And wish I'd space this a little better, but I want to draw this down here. Maybe that'll work. So I got, let's see, 64.7 and 241.5. I know that's a little hard to see. I hope you guys got plenty of room on your paper, but I'm going to use this room for my knowns. Okay, so that x thing, that x component I just erased was 64.7 meters per second. And that is, at the moment, all I know in the x direction. I know I have some values down here as far as how far away this ship is. That is horizontal information, true. But it's not necessarily where this projectile ends up. We're assuming the projectile overshoots that. So at the moment, that's all I have horizontally. Vertically, what I know the initial y velocity, or Vy naught, either way, was 241.5. Leave my units off, but these are all standard metric units. And that appears also to be all that I know. So other things I know about the y direction that I can just always throw in there is gravity. Well, I guess I'll put the units on there too. And now I just need to decide which question I want to answer first. How far from the ship is the projectile, or how far from the mountain? Doesn't matter which one I do first. I'm going to go ahead and try to figure out how far from the ship this projectile hits. So if I want to find how far from the ship it hits, I need to know the horizontal displacement. And then I will compare to 2,500 plus 610, because that's how far away the ship is. And just like the last problem, I could solve this if I just knew the time. If I knew how long this projectile were in the air, then I could solve this problem as to how close it is to the ship. So, y information, I got to get some help and figure out the time this projectile is in the air. And you could do two things. Sometimes people just like using a final velocity of 0. I could say the final velocity at the peak is 0 and solve for the time it takes to get to the peak, and then just double that time. So full time would be double half of it. But that's one extra step, doubling a number. So instead, I'm going to say the final velocity, I should have done white, is negative 241.5. As it is hitting the water, again, it's symmetrical. It's going to have the same velocity going down as it did originally going up. So the final velocity is negative 241.5 at the end of its flight. Again, that's right as it's hitting the ground / water, not after. Because, of course, that would be from a whole different force besides gravity. We couldn't use that acceleration if it's already hit the ground. Okay, so we're using the idea that projectiles are symmetrical, and we can just find the full time that this projectile is in the air. Look at your kinematics list. Find the kinematics that's got all that stuff, which really is just the first one. And solve for time. So that just tells me that the projectile is in the air for its full flight, 49.2 seconds. Okay, now this is a missile, so makes sense that it's a little bit longer than just something falling off the table. Now I can plug that into the x direction, and the same amount of time that it's traveling up and down, it is also traveling to the right. And in the x direction, I always use velocity as displacement over time. Sorry. Solve for my displacement. And I get 3,183.2 meters. That's sort of the range. That's how far it goes to the right. And I just wanted to compare that to where the ship is, which looks like it's pretty close. The ship was 2,500 meters plus an additional 610 meters. So if I just add those two up, again, 2,500 to the mountain plus another 610, the ship gives me 3,110 meters. So that's how far away the ship is. This is how far away the missile actually goes. So it's pretty close, 73.2 meters off. I guess pretty close if you're considering the whole thing was 3,000 meters. But we overshoot the ship by that much. Okay, so quick recap as to how we figured that out. We used the vertical information to figure out how long the projectile was in the air. That same amount of time can be applied to the x direction, which is 49.2 seconds. And then knowing its x velocity and the amount of time it is going 64.7 meters per second to the right, I can figure out the x displacement, 3,183.2 meters, subtract from where the ship actually is, so we were 73.2 meters off. All right, that was just part one. And not all your homework problems are this long, I promise. Part two is how high above the mountain is the missile. And we can't assume that the mountain is like halfway, like right where the peak is of our trajectory anyway. And the picture doesn't look like it is, so just be careful you don't do that. I'm going to erase some of this, give myself a little more room. This 49.2 seconds is not relevant anymore because obviously it'd be less than 49.2 seconds to get that far. I'm going to erase my time. This final velocity is not relevant here either. So starting out with still the same basic information, I know my x and y velocity components, I know gravity's there, that's about it. This time, I just want to figure out a vertical piece of information. I want to figure out the vertical displacement and compare it to this mountain height of 1,800 meters. So at the moment, I'm just kind of stuck in the vertical direction. I just don't know enough information vertically to solve for that vertical displacement. But just like usual, I can get the time it takes the projectile to get right here using horizontal information. I can find the time in one direction, use that time in the other direction. And this time I do know the horizontal displacement being this 2,500 meters. So now I could use the horizontal info to find out how long it takes the projectile to get here, 2,500 meters to the right. So $2,500 divided by 64.7, 38.6. So it takes 38.6 to go 2,500 meters to the right. In that same amount of time, it'll be right above the mountain. So I'm going to use that over here. And now I can use a kinematic again, but this time one that has displacement in it. So it's going to be this one. Don't forget gravity is negative, certainly important we're subtracting that part. Okay, and I get (2,013.65 meters). Again, that's displacement, that's final minus initial. Makes sense that it's positive. It is above the ground at that moment. The mountain itself was 1,800 meters tall. So minus the mountain height, we get (213.65 meters above the top of the mountain. All right, again, I know it's a long problem. The more you practice, though, the quicker these will get, I promise. Did a lot of over-explaining here. Again, key ideas, find your components of your initial velocity first. Never, ever deal with a given initial velocity that's at an angle. Find the components first. You will always use the components and not the original velocity. Very often, you need to find the time in one direction and plug it into the other. Always are using velocity as displacement over time for horizontal information, and we're always using the kinematics for vertical information.